In the name of Allah, the most gracious, the most merciful, all praise is due to Allah, and peace and blessings be upon the Messenger of Allah, our Master Muhammad, and upon his family and companions altogether. Now as for the time, indeed mankind is in loss, except for those who have believed and done righteous deeds, and advised one another to truth, and advised one another to patience. For setup, we use the same method as before. First, calculate currents under normal conditions. Then set a higher value to prevent incorrect earth volt relay operation. The pickup current for the earth volt relay is typically 10% to 30% of the maximum load current. To increase sensitivity, reduce this percentage. For example, set the earth volt relay at 30% of the maximum load current, ensuring the pickup value is higher to avoid incorrect operation. Typically, the pickup current is 10% to 30% of the maximum load current. To increase sensitivity, adjust the percentage accordingly. To prevent these currents from causing misoperation of earth volt relay, the earth volt relay pickup current is set 10% to 30% of the maximum load current. To increase sensitivity, reduce this percentage. For instance, set regular earth volt relay at 30%, sensitive or standby, earth volt set at 15%, neutral current alarm at 10%. Choosing the same percentage is not necessary. It clarifies context. Note the primary pickup current for earth volt relay. Percent of the value of the crush block. As for the sensitive earth volt or the standby earth volt, it is set at 15% of the maximum load current, while the neutral current alarm is the most sensitive, set at 10% of the maximum load current. It is not necessary to choose the same percentage we mentioned earlier for setting the earth volt. Rather, this is to give a clearer picture of the surrounding context. We should also pay attention to the value of the primary pickup current for the earth volt relay. The pickup current for the earth volt relay that has been chosen should not exceed the maximum earth volt value for the current that will pass through the neutral earthing resistor during the return of the fault current to its source. Pickup current must not exceed max current through NER during fault return. Calculate NER capacity. 20 ohm NER on 11 kV side handles 317 amperes. Pickup value should be 10% to 30% of max load current, not over 317 amperes. If the pickup current is set higher than the NER's capacity, it may burn out. With a 20 ohm NER on an 11 kV transformer, the capacity is 317 amperes. The pickup value for the earth volt relay should be 10% to 30% of the maximum load current, not exceeding 317 amperes. Time grading for the earth volt relay is like overcurrent. Choose definite or inverse time characteristic. Study the earth volt relay independently from the overcurrent relay, as they are unrelated protection types. The pickup value for the earth volt relay should be 10% to 30% of the maximum load current, not exceeding 317 amperes. Time grading for the earth volt relay is like overcurrent, no difference. Choose definite or inverse time for the earth volt relay. Study it independently from the overcurrent relay, as they are unrelated. The pickup for feeders 1114 is 30% of the maximum load current, 100 amperes, making the primary pickup 30 amperes, with a disconnection time of 200 milliseconds, using the definite time curve. As for how time grading works for the earth volt relay, it is exactly like overcurrent. There is no difference at all. You can choose the characteristic for the earth volt relay either by selecting definite time characteristic or the inverse time characteristic. For instance, if we go back to the previous example, we conduct a study of the earth volt relay completely independently from the overcurrent relay, as these are two different types of protection and have no relation to each other. Therefore, the earth volt pickup value for feeders 11, 12, 13, and 14 is 30% of the maximum load current, which is 100 amperes, making the primary pickup value 30 amperes, and the disconnection time here is 200 milliseconds, as we chose the definite time curve. As for the airfold pickup value for this bus section, it is set at 30% of the maximum expected load current, which is 200 amperes. Therefore, the pickup value is 60 amperes, and the disconnection time is 400 milliseconds, as we added an additional 200 milliseconds to the initial time. As for feeders 1 and 2, the pickup current value is 30% of the expected 400 amperes passing through each feeder. Therefore, the pickup current value is 120 amperes, and the disconnection time is 400 milliseconds plus 200 milliseconds, which was chosen as the time grading between each phase and the next. Thus, the total disconnection time is 600 milliseconds. For this bus section, the pickup current for the earth volt relay is 30% of the transformer's rated current, 1312 amperes, making it 393 amperes. The NER handles only 317 amperes, 11 kV, 3 Setting 393 amperes is risky, so assume 300 amperes to protect the NER. Disconnection time is 800 milliamperes, 600 plus. Now, notice with me that the current that the NER can handle is only 317 amperes, as calculated before. 11 kV divided by the square root of 3 divided by 20 equals 317 amperes. So it becomes very dangerous to set this value as the pickup. Therefore, we should assume that The pickup current value here is only 300 amperes to protect the NER. The NER here cannot handle a value higher than 317 amperes, otherwise it will burn out. As for the disconnection time for this bus section, it is 600 milliseconds plus 200 milliseconds, which equals 800 milliseconds. Regarding the pickup setting current for the secondary side of the power transformer, it is equal to the same pickup setting current for the bus section, which is 300 amperes. But what is different here is that the separation time is equal to 800 milliseconds, which is the separation time of the base section, and we add 200 milliseconds to it. So the total time becomes 1000 milliseconds. As for the third and fourth feeders, each one of them can bear 400 amps, and thus the value of the pickup current for each one is 30% of the 400 amps, which is equal to 120 amps. 400 amps equals 120 amps, okay. The disconnection time is only 200 milliseconds because there is no coordination between it and any subsequent feeder. Therefore, the table summarizing these calculations is as follows, and this table is provided to the protection engineer so that he can input these settings into the relays. Using overcurrent and earth volt relays is ineffective to cover all fault cases, as their capacity to protect the power system remains limited, because there are some faults that the overcurrent and earth volt relays cannot handle. This means it may misoperate on an external fault. It can malfunction with a parallel line supply in ring networks or with a multi-feed source. Let's analyze this case to show the overcurrent relay's inadequacy. If a generator feeds a parallel line with 2 circuit breakers on each line and overcurrent relays at both local and remote stations, a fault on transmission line 1 will be fed from 2 directions. Consequently, all 4 overcurrent relays will sense this fault. The fault on transmission line 1 should disconnect it by tripping these 2 circuit breakers based on selectivity. Why have a parallel line if a fault on one trips both? The first relay to sense the fault will be R1, detecting the highest fault current. We installed 2 circuit breakers and used overcurrent relays on each line at both local and remote stations as shown in the diagram. If a fault occurs on transmission line 1, it will be fed from 2 directions, causing all 4 overcurrent relays to sense the fault due to the series connection of CTs. The fault should lead to the disconnection of transmission line 1 by tripping the 2 circuit breakers, ensuring selectivity in the protection system. The first relay to sense the fault will be R1, as it detects the highest fault current due to lower impedance in its path. Notice the line length. Higher current flows through lower impedance. R1 trips while R2, R3, and R4 remain closed. R2 should then trip to take transmission line 1 out of service. The fault is supposed to be on transmission line 1, so transmission line 1 should be disconnected by tripping these 2 circuit breakers, based on the fundamental requirements of the protection system, which is selectivity. What is the point of having a parallel line if a fault occurs on one of the lines? Both are tripped. The first relay to sense the fault will be R1, as it detects the highest fault current among the 4 relays. This is because the impedance in the second path is higher than in the first path. The higher current flows through lower impedance. Now R1 has tripped, while R2, R3, and R4 remain closed. R2 should trip to take transmission line 1 out of service, which is the line that experienced the fault. However, if R3 and R4 trip during this fault, both lines go out of service, and we will lose the load supply due to a single fault on the first line. R3 will not operate initially because it is the only one that will see the fault from the farthest point. The issue is with R2 and R4, as they see the fault at the same distance and with the same impedance. So who will trip first? If R3 and R4 trip during this fault, both lines will go out of service, and we will lose the load supply from a single fault on the first line. R3 will not operate at first as it sees the fault from the farthest point. However, the problem lies with R2 and R4, as they see the fault at the same distance and with the same impedance. So, who will trip first? We want R2 to operate and not R4, but what will guarantee that R4 does not operate? Thus, we must find a way to prevent R4 from operating incorrectly, using the principle of directional protection in the overcurrent or earth volt relay. But the problem lies with R2 and R4 because they see the fault at the same distance and with the same impedance. So who will trip first? We want R2 to operate, but how to ensure R4 doesn't operate? We must prevent R4 from operating wrongly. This method determines fault direction using directional protection in overcurrent or earth volt relay. This protection uses a relay, ANSI code 67 for directional overcurrent or 67N for directional earth fault. Each relay trips only for faults ahead, never behind, even if current exceeds 1 million. This is protection in the CANT or the ELI. This is represented by the ANSI device code as 67 for directional overcurrent or 67N for directional earth fault. The essence of this principle is that each relay can only trip for the fault in front of it. It will never trip for a fault behind it, even if the current value exceeds 1 million. Faults are either forward or reverse. Replacing R2 and R4 with 51 non-directional phase overcurrent means it trips for any fault. With 67 directional phase overcurrent, it trips only for forward faults. R4 won't trip for reverse faults, only R2 will for forward faults. Forward faults mean current flows towards the transmission line out of the bus bar. Reverse faults mean it comes from the transmission line. This is called directional phase overcurrent, which trips only for forward faults. R4 didn't trip because it detected a reverse fault, while R2 tripped due to a forward fault. The relay determines fault direction based on current flow. Forward faults direct current towards the transmission line, while reverse faults direct it towards the bus bar. Directional overcurrent relays are more reliable and selective than non-directional ones, especially for critical loads. The question remains the same. What is the criterion for deciding whether this fault is forward or reverse? The term forward fault here means that the current flow was directed towards the transmission line, meaning it is coming out of the bus bar and into the transmission line, while a reverse fault means it is coming out of the transmission line and into the bus bar. The directional overcurrent relay is distinguished from the non-directional overcurrent relay by its increased reliability. How does the relay understand the current flow direction? The current lags behind the voltage by 20 to 30 degrees. The directional earth fault relay increases reliability. How does the relay know the current flow direction? In normal conditions, current lags voltage by 20-30 degrees. If current reverses at fault, it leads, indicating reverse fault. If current lags before and after fault, it is forward. Thus, track current direction to determine fault. In normal conditions, current lags voltage by 20-30 degrees. So, if there is a reversal in the direction of the current at the moment of the fault, this means that the current has become leading, indicating that the fault is reversed. However, if the direction of the current remains lagging before and after the fault, this means that the fault is forward. Therefore, we can determine whether this fault is forward or reverse by tracking the direction of the current. How do we track the direction of the current? By tracking the angle between it and the voltage, which serves as a reference point. We determine the current's angle. For instance, if asked, how far is it from Jerusalem? You need a reference, like from Amman, to answer 70 kilometers. Similarly, determining the current's angle requires the voltage's angle as a reference. The voltage signal, known as the polarizing signal, can be a polarizing voltage or current, or both. However, voltage is usually preferred as the reference. So I would say, regarding the capital Amman, you would immediately tell me that the distance between the holy city of Jerusalem and the capital Amman is 70 kilometers. Notice that we could not accurately determine the distance without first establishing a reference point. Similarly, I cannot determine the angle of the current without first establishing a reference point, which is the angle of the voltage. In this case, we call the reference voltage signal a polarization signal or polarization voltage, knowing that the polarization signal can be used either as a voltage, in which case it is called polarization voltage, or as a current, in which case it is called polarization current, or both can be used together, i.e. polarization and e-polarization, but usually it is preferable to use the voltage as a reference point more than the current. Current disappears when the circuit opens and returns when it closes, while voltage is always present. A stable reference point is preferable, like a rock, not a cloud. For directional protection in overcurrent and earth fault, two inputs are needed, from CT and VT. Non-directional overcurrent needs only one input from CT. In directional cases, voltage is essential. In non-directional, it's only for measurement if present. Directionality is clearer through this phasor diagram, showing vectors VA, VB, and VC. We need two analog inputs from CT and VT, while non-directional overcurrent needs one input from CT. In the directional case, voltage must be present. Voltage isn't needed in non-directional overcurrent. If present, it's for measurement. Directionality is clearer in this phasor diagram with vectors VA, VB, VC. Assume resistive load, IA aligns with VA. Placing VA and IA in phase simplifies info. IA is aligned with VA or leads VBC by 90 degrees. Directionality is clearer in this phasor diagram with vectors VA, VB, VC. Assume the load is resistive, meaning IA aligns with VA. Aligning VA and IA simplifies information. IA can be in phase with VA or lead VBC by 90 degrees. If IA's direction during a fault matches VA, the fault is forward. If IA reverses, creating a 180-degree phase shift with VA, the fault is reversed. The question is, what limits keep the current or its components directed forward towards the reference voltage? Analyzing the current, it has two components. One on the positive x-axis in the direction of VA and another on the positive y-axis. If the current is in the same direction as VA, this shows a forward fault. However, if the direction of the current is reversed and it goes in the opposite direction, this shows a reverse fault. What are the limits for current or its components to stay forward towards reference voltage? Analyzing current, it breaks into first on positive x-axis towards VA or reference voltage, and second on positive y-axis. If the current is at this angle, it breaks into first directed positively towards reference voltage and second directed negatively. What are the limits for current or components to stay forward towards reference voltage? Analyzing current, it breaks into first on positive x-axis towards VA or reference voltage, and second on positive y-axis. If the current is at this angle, it can also be broken down into two components. The first component is directed positively towards the reference voltage, and the second component is directed negatively. Notice that its focus is on the component that is on the positive x-axis. As long as the current is being analyzed, if it shows even a 1% component towards the positive x-axis, it is considered to be in the forward direction. Therefore, the limits of the angle of the fault current that we consider to be a forward fault, meaning it is within the forward zone, start from 90 degrees passing through 0 to negative 90 degrees. The current can never lag behind the voltage by an angle greater than 90 degrees and still be considered a forward fault. As for the limits of the fault current angle, we consider a reverse fault, meaning within the reverse zone, it starts from 90 degrees, passing through 180 to negative 90. Notice that when the direction of the fault current is in this way, it can be analyzed into two components. One component is directed. When the fault current flows this way, it splits into two negative components. A 30-degree delay in current shifts the forward zone limits by the same angle. And the other towards the y-axis, the negative. A 1% fault current shows a reverse zone fault. A 30-degree delay shifts forward zone limits to start at 60 degrees to negative 120 degrees. A 60-degree lead shifts them to start at 150 degrees to negative 30 degrees. An 89-degree fault is forward, 91 degrees is reverse. This line stays perpendicular to IA, and thus the limits of the forward zone start at an angle of 60 degrees to 0 to an angle of negative 120 degrees. If the current is leading by an angle of 60 degrees, the limits of the forward zone also stay perpendicular to it. So the limits of the forward zone in this case start at 150 degrees to 0 to negative 30 degrees. Note, if the angle of the fault current is 89 degrees, it's in the forward zone, and if the angle of the fault current is 91 degrees, it's in the reverse zone. Note, 89 is forward and 91 is reverse. If the angle of the fault current is 89 degrees, it is forward, and 91 degrees is reverse. The proximity of these angles can confuse the relay. To prevent relay malfunction, the angle should be 85 degrees, ranging from 85 through 0 to 85 forward, and 95 through 180 to 95 reverse. Rows. And 91. To avoid any malfunction of the directional protection relay, it is recommended that this angle should not be 90 degrees, but rather 85 degrees, ranging from 85 passing through 0 to 85 in the forward zone, while the limits of the reverse zone range from 95, passing through 180 to 95. The area between them is called the dead zone. A truly national renaissance.